right, so let's talk about definite integrals and antiderivatives. So what I wanted to start off with is a recollection as to why we're doing this, which would be a good thing, right? What is the area under the curve? From A to B. And here we go. This is my curve, f of x. And this is going to be A. And this is going to be B, obviously my endpoint. And this is the area under the curve. Now, last time, or on the video, I'm hoping that you saw that that's just the integral, right? The integral symbol from A to B of, if this is f of x, right? It's going to be f of x times dx, where this is the function height and this is the width, right? So it's length times width, which is just the area of a rectangle. But how many rectangles are there here? Infinitely many, right? And that's for a less than b but greater than 0, right? So I've got it on the right side. And what is this equivalent to in limit speak? The limit as n approaches infinity, where n is the number of rectangles, right? And we use the summation symbol to sum up the rectangles, right? From I equals 1 rectangle to how many? N rectangles of f of x sub I times delta x, right? Where this was the length and this was the width, right, of the rectangles. And what was delta x? How did we figure out what delta x was? Where delta x is equal to, they said quietly for those who might be listening to this recording, b minus a over n, the number of rectangles. And we're going to have to know these facts as we go over the properties of integrals here. Integral is nothing more than an area under the curve from point A to point B. Okay? So order of integration here. So what's the difference? Right, so I'm just going to draw a real quick picture here where I have my f of x, and it doesn't matter what well, I'm going to make it try to look like the original one. I'm going from A to B, that's the area. So I'm saying that what happens when I integrate, or to find the area under the curve from A to B, instead of going from A to B, I go from B to A. What has in this expression up here changed? The delta x has changed, right? Because if you're going from B minus A, it's a negative, right? It's like it's been at the negative area. So you can say then that delta x here, which is b minus a over n, becomes what sign? Negative, right? So when you integrate from left to right, it'll be positive if it's above the x-axis, and if you integrate from right to left, it'll be the opposite value of integrating from left to right. Make sense? Because the delta x becomes negative. What about this case? There is no area, right? Because have you even gone anywhere? So, but what in that limit goes to 0? Delta x again, right? Because in this case, delta x, which is equal, oops, I can't write delta x. Delta x equals b minus a over n, but a is equal to b. is equal to A, right? So you would say that B is equal to A, and so that's going to be A minus A over N, which is just 0. So the delta X becomes 0. So you can't have any area if you're starting and stopping in the same spot. I hope that makes logical sense to everybody. Very visual thing. All right. All right, what about a constant multiple here? What this property says is if I wanted to find the area under k times my function, which is the orangey looking, if I wanted to find that area, could I first find the area under the blue function and then multiply it by 2? So what could I do with that constant? I could pull it out in front, right? So that's the constant multiple property. Just like derivatives, right? You can pull a derivative, you can pull a constant out in front of a derivative. This is pretty logical. Everybody get that? Sum and difference. So let's say you have a function that's defined as f of x plus g of x, which is the green function here. This property states that if you find the area under the green function, it'll be equal to the same thing if you found the area under the blue function and added it to the area under this orange function. Does that make sense? That's pretty logical also, I think. So you can bust it up. Your book doesn't have these graphics. Oops, was I supposed to scroll down? So I like the graphics. They're very explanatory. Okay. This says, let's say I'm going to find the area from A to B. So I go from the area from A to B, and I go then from B to C. Does it make logical sense then that that would equal the integral then, or the area under the curve from A to C? Yes. I hope that's logical to everybody. Max-min inequality. Now, what is this? What does this represent here? Okay, well, we have a minimum. Well, what are we doing with the minimum value? What are we doing? Multiplying it by the, would you call this a width? And this a length? So what is this? Area of this is the area of the rectangle formed by the minimum of f. Does that make sense? That's going to give you an area. It's going to give you a rectangular area that's going to be the smallest rectangular area, right? Because you've got the lowest y value, and you're using that to create an area here, this area. Okay, then similarly, and I don't know if I can find a color that's close. I'm thinking that's it. What's this represent? That's pretty close. Time to stand up. You were fading. You were fading. All right, so where's the max occur? Right here, right? So what does this then represent? This is the length times the same width, right? So this is the area of the rectangle formed by the maximum. max-min inequality says is that the area of the under the curve, the blue, has to lie between those two areas. So this is the area of the biggest rectangle, and this is the area of the smallest rectangle. And this, the actual area itself, has to lie between the big one and the little one. To me, that's pretty logical. Yes.
This is with the absolute right?
Yes.
Okay.
Over the interval. Yep.
So that's with, so I understand it's height, and so it's width, A to B.
Yes. Yeah. All that says is that the rectangle created by the minimum value of f times the width, and the rectangle created by the maximum value of f will create two rectangles, and the area of the curve has to lie between there somewhere. All right, so let's see how this all works. Oh, I got another one, huh? Sorry. Additivity. Down further. Did I already do this? Okay. Sorry. Right. This is everybody's favorite property. Domination. Yes, because everybody giggles. All this property states is, if f of x is greater than g of x over the entire interval, would that happen here? F of x is all the y values are bigger than the y values on the g of x, right? If that's true over the entire interval, greater than or equal to, I guess, then the area under f will always be bigger or equal to the area under g. So that means the area under f dominates the area under g. Makes sense. It's logical. Oops, I did it again. Special case. Now, why would I talk about this? What's g in this case? 0. So let's draw a picture for that. What would happen here? We'd have some f of x is greater than 0, right? There it is. There's my f of x greater than 0. And I'm going to go from a to b. And what's my second function? It's g of x is equal to, we'll just say g of x is equal to 0. What has to be true of the area? The area has to be greater than 0 because it's above the x-axis, right? All right, so I was excited to get to this. This is kind of fun, the stuff that we do here. So this says the integral, you're given that the integral from 1 to 3 under f is equal to 6. And then the integral from 3 to 7 is 9. And then the integral from 1 to 3 over g of x, the area under that curve from 1 to 3 is negative 4. What does that mean? That this is negative. What is below, right? Okay, so let's see if we can use some of the properties here. It's what? That's right, Mitchell. We're going to pull out the 3. So we can say that this is equal to 3 times the integral from 1 to 3. Which property is that? The constant multiple property. And do we know what this is? They told us. So that would be 3 times 6, which is 18. Right? This is an area, so it's really unit squared. So what can we do here? We can split it out and pull out. Okay, so we'll go 2 times the integral from 1 to 3 of f of x dx minus, help me, 4 times the integral from 1 to 3 of g of x dx. Right, and they told us what these values were, so this is going to be 2 times, we said 6, right? 6 minus 4 times negative 4, so that's going to be 8 plus 16. I'm sorry, what?
12 plus 16.
12 plus 16?
Yeah.
Which is?
No.
Yes.
Yeah.
What is going on?
Pretty close.
You've got me worried.
It's 28.
Okay. I was trying to. Did I hear something else first?
You said 8.
You said 8 when you.
Oh,
And
okay.
then I said 12 and then I got confused.
Okay, I'm sorry. So that was a funny moment for those of you who will be listening to this later. And no, none of us have lost our mind. Well, maybe me. Okay. Sorry about that. That was silly on my part. Well, you know we have to have fun on a Friday. Okay, here we go. I'm try this color. All right. What is this one?
Oh, I did backwards.
Okay, go ahead, Olivia. What do you get? Integral.
It's the one where it's like 8 to from 1 to 3.
What?
From 1 to 3, plus the integral of fx dx from 3 to 7.
Yep. What property was that? Additivity. And this was 6? Not 8.
6.
I was adding instead of multiplying. You know that's where my brain was. Okay, plus
9.
9, which gives me everybody 15. Hey.
Well, the answer is always 18.
Right, you have to go 18. All right. Is that green?
That looks green. It's like a weird between green and brown. On the board.
Do you see that?
Other boards.
Here we go. What's this? He's not that colorblind. Okay. These are flips. So I can say negative of the integral from 1 to 3 of f of x dx, and we know that's 6, right? So this is negative 6. That's pretty easy stuff, isn't it? And the first part of the homework is that. Yeah, I knew you'd like that. All right. Now this is where it gets a little bit intense. Gnarly is a good word. Who said that, gnarly?
Who said gnarly? Who served?
Who wasn't that, Sam?
It was Alex.
Wait, what?
Who said gnarly?
Somebody heard it, right?
I didn't hear gnarly.
Miss Mueller was the one who said gnarly. She said gnarly is a good word.
Oh my gosh, okay.
We're all kind of. I was more than just a little mad science.
All right, gosh, we've had a good laugh. Ben and Brandon, sorry.
And Timmy.
You always forget Tinny.
And Timmy.
Don't forget Timmy.
Oh, okay, Timmy is at the University of Tennessee. Boo. Anyway. All right.
We're all going to go to Georgia Tech every single one.
No. I'm just teasing. If you have to go where you're happiest. That's what I really believe. Okay. Average value of a function. Average value of a function. When finding the average of a bunch of numbers algebraically, what do? You add them up and then divide by a number, right? What if we wanted to find the average value of a function? Well, what are values of a function? They are the y values, right? So over an interval, let's say from a to b, let's say I wanted to add up all of the y values, right? So I've got from a to b, this function has a bunch of y values that I would like to be able to average. Well, how many y values are there? Infinitely many. But let's not bite off choose.
Okay.
All right? So let's add up n of them first, shall we? And we'll say that this is the average. We'll add them up and then we'll divide by n, right? We'll say the average value of n of them. Hang on. Is going to be the sum of all of the n ones, right, divided by how many n of them, right? So then that's going to be, well, what's the first one going to be? F of, you could say f of a, right? But we could say f of x of 1 and not limit ourselves to just this interval, right? Plus f of x of 2 plus dot, 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 plus f of x of n, and that would be the last one. All divided by n of them, right? Now last time I hope you guys discovered that, gosh, when you're adding up a bunch of numbers, is there an easier way to write this?
Yeah.
Summation. So we could say that's the summation from I equals one of the numbers to n of the numbers, and that's going to be f of x sub I, and then I'm going to pull the 1 over n out in front. Is that okay? Now, what are you thinking when you see this? Besides,
Integral.
okay, you're thinking that might be an integral. So you're thinking, logically, correctly, that it looks a lot like what? The sum of f of x of I times delta x, right? But what's missing? The delta x, right? If only there was a way for us to get delta x in there. Well, what is delta x? B minus a over n. Do we have anything in that expression that might help us? 1 over n. What happens if we solve? What if we solve for 1 over n?
Well, n equals b minus a over x.
N equals
b over a minus x. Minus delta over.
over delta x, right? Yeah, I like it, right? I knew what you meant. And so what does 1 over n then equal? Delta x over b minus a. So could I substitute for 1 over n and say delta x over b minus a times the sum from I equals 1 rectangle to n, or n from, not rectangles, but I equal 1 y value to n y values of f of x of I. Did I do that? Now the delta x has arrived on the scene. Yes, and we're going to put it in because we're going to, in our class, we're going to assume that this delta x is constant, so we can bring it into the expression. And so we can say that this is equal to 1 over b minus a times the sum of I equals 1 y value to n of them of f of x of I delta x. Getting closer. But remember, this is for n y values. I need how many y values? Infinitely many. So now I'm going to take the limit. So I can say the average y value over the interval from a to b is equal to the limit as the number of values goes from 1 to infinity, right? As n goes to infinity of, yep, 1 over b minus a times the integral, oops, nope, sorry, not integral yet, sum, we're going to get there, x of I delta x, and we're going to go from I equals 1 one y value to n, and we're taking that to infinity. Now 1 over b minus a is going to be a constant, so I'm going to pull that out in front. And so what is this that we know now? That's the integral. So this is equal to 1 over b minus a times the integral from a to b of f of x dx. So I'm saying to you that the average y value, or average f, over the integral from a to b is going to be the area under the curve divided by b minus a. It's almost like you're summing up all the y values and dividing by the number of them. Almost, right? With the Roman s for sum. Now, sometimes people will, pardon the pun, sometimes, they'll write it like this. So you can see it, you've seen it like that. I see it like that sometimes, okay? What? I'm distracted by the head bobbing. Moving right along. The mean value theorem for integrals. You knew that there had to be a mean value for integrals because there was one for derivatives, right?
Of course. Right.
Right, okay, so this is at the moment, I'm going to ask you to take out that second piece of paper.
Beans? You know Pythagoras was afraid of beans. That's what happened.
Everybody needs to get this sheet of paper out.
Apparently Pythagoras was afraid of beans. He told his followers where to like abstain from beans.
And I don't have beans, so we're going to have to use Smarties. Okay?
Is it long enough?
All my dirty laundry is going out. That's crazy, teacher. Can't add and subtract.
Do we each get 3 things?
I knew you could do it.
Yeah, I just wanted to make Lucky feel better.
I said,
Yeah.
Public school.
okay, I watched that. Oh god.
Except for 1 year.
So, what you need to do is let's read the instructions on the top. What's it say?
Playing beans.
Except for playing with Smarties.
Smarties here, actually, which are better.
I learned about this yesterday. Or not yesterday, but the day before. Wednesday, right?
Well, this is.
I went to my conference and I learned about this. I think it's pretty cool. So, I didn't have time to buy beans. I figure Smarties will work, right?
I like Smarties.
Most people do. Because you can eat them. And what I used were beans you could eat during my little session that I was in. All right, so it says fill instantaneous slope, right? So the mean value theorem for integrals doesn't have anything to do with slopes, but has to do with areas. Okay? So everybody's area almost filled up?
I need to have one.
You don't have to be really precise.
Precise.
Okay?
No, I missed one. No, I missed one. Okay. I handled it.
She ate it. All right.
I don't think I have one quite smart.
There's a Smartie like right down there. It like rolls all the way. It's white.
All right, so everybody should have their area filled with Smarties, yes?
Thank you, Olivia.
Now, what I want you to do is to rearrange the Smarties in that same interval from A to B to be a rectangle.
Just any rectangle.
Well, it can go above the curve, right? It can probably go above the curve to be a rectangle. You're going to take the Smarties and make a rectangle. So you're going to fill up a rectangle to a certain height with the number of Smarties you got right there. You don't add any more Smarties.
One extra Smartie.
There we go. I like that. All right. So here we go.
Let's pretend this guy wasn't here.
Oh, that was perfect. You do.
Okay. I want you to
I got it.
label the place where it intersects the function.
Oh, it's perfect too.
Label that point where it intersects the function right here. Label the point.
Top here.
And label this point on
Top of your box.
top of the box where it hits the function. Alright, so once you've labeled it, remove the Smarties and keep a visual image of what those Smarties look like, right? That's the area of a rectangle, right? Okay? That height right there is the average y value of your function. Now, why does that work? Because what was, oh, I gotta